The hydraulics are freezing up again.
I see it. Are we losing power to the array?
Fluctuating by 10%.
The wind is shifting the grid. Hold fast.
Adjusting stabilization servo. Check the azimuth now. Look here. The azimuth readings are inconsistent past 50 miles. We need better filtration.
Captain, the issue isn't the filtration, it's the sighting. We need elevation.
January 17th, 1941. A bitter wind swept across the outskirts of New York, rattling the skeletal framework of a lone radio tower. Snow lay thick on the ground, muffling footsteps of engineers and assistants as they trudged between cramped laboratories. Inside, the hum of early electrical machines filled the air, mingling with the faint scent of solder and ink. A young technician adjusted dials on a massive IBM tabulating machine, fingers trembling from both cold and anticipation. Outside, radar antennae spun slowly against a gray sky, scanning for invisible patterns, searching for signals the human eye could never see. The military had demanded a weapon against uncertainty itself, weather. And here, in this frozen lab, that challenge was being met with wires, circuits, and raw ingenuity. Through the frosted glass, scientists glimpsed storm fronts creeping over the Atlantic, each cloud a potential threat to naval convoys, troop movements, and the fragile balance of global power. Every calculation mattered. Every forecast could be the difference between life and death. This was the dawn of a new kind of warfare, one fought not just with guns, but with information. By early 1941, the United States faced a surprising vulnerability. Despite its industrial might and vast coastlines, the country lacked a coherent, modern system for weather forecasting. Meteorology had advanced in Europe, where nations like Germany and Britain were already using a combination of observation networks, rudimentary radar, and naval reconnaissance to anticipate storms and plan military operations. In America, the National Weather Service still relied heavily on surface observations, sporadic balloon launches, and telegraph reports. Forecasts often arrived too late, incomplete, or contradictory. The stakes were rising. Across the Atlantic, war had engulfed Europe, and the German Kriegsmarine was already demonstrating how meteorological intelligence could tip the scales. Submarines prowled the North Atlantic, exploiting weather patterns to evade detection. The Allies, meanwhile, struggled to coordinate convoys in unpredictable conditions. Every miscalculated storm cost ships, cargo, and lives. Yet in the United States, military planners had no equivalent advantage. The technological landscape reflected this gap. Radar, radio detection, and ranging was still an experimental field. British scientists had achieved early breakthroughs, detecting aircraft and ships using radio waves, but their applications to weather were just beginning. In the United States, engineers understood that radar could, in theory, track storm systems, but practical implementation was untested. Early equipment was cumbersome, delicate, and required constant calibration. The antennas needed to be massive, the machines power-hungry, and the operators highly trained. Few facilities had the resources to build, maintain, or interpret them effectively. It was against this backdrop that IBM, then known primarily for business tabulating machines, entered the fray. International Business Machines had spent decades developing electromechanical computers capable of processing massive amounts of data with remarkable speed. In peacetime, these machines counted census data, managed payrolls, and tracked inventories. But military planners now envisioned a different application, feeding real-time weather observations into a system that could analyze, predict, and ultimately forecast storm patterns with unprecedented precision. The challenge was enormous. Weather is chaotic, fluid, and highly variable. To capture it, hundreds of data points, temperature, pressure, wind direction, humidity, needed to be recorded, transmitted, and processed daily. Government agencies began to recognize the urgency. The Army Signal Corps and the Weather Bureau established preliminary committees to explore radar applications for weather tracking. Navy officials advocated for monitoring Atlantic storms, noting that transatlantic convoys and planned troop deployments could be devastated by unanticipated gales. Scientists debated whether existing technologies could be adapted or whether entirely new systems had to be built. Equipment shortages complicated matters. High-quality vacuum tubes, precision resistors, and powerful motors were all in demand, and the manufacturing pipeline had not yet fully shifted to wartime production. Despite these hurdles, momentum built. A handful of forward-thinking engineers at IBM and the Weather Bureau proposed a network of radar stations along the eastern seaboard. These stations would feed continuous data into IBM tabulating machines, which could then calculate the movement of storm fronts and predict conditions up to several days in advance. It was an audacious plan, bridging industrial computation and meteorological science, and it would require cooperation between scientists, military officers, and private industry, a collaboration unprecedented in American history. The human element cannot be understated. Weather forecasters were under immense pressure. Each telegram of wind readings, each barometric measurement, was scrutinized. Errors could mean ships lost at sea, air crews caught in deadly turbulence, or training exercises canceled at the last minute. Engineers faced mechanical failures and electrical fires in freezing conditions. Yet in the labs and early radar sites, there was a sense of purpose, almost exhilaration. They were pioneering a new form of warfare, one fought with data, circuits, and human ingenuity. By mid-January 1941, sketches of the first operational radar stations were being finalized. IBM machines were reconfigured, engineers trained, and test sites chosen along the Atlantic coast. The United States was on the cusp of a technological leap, moving from ad hoc observation to predictive meteorology. But significant obstacles remained. The machines were temperamental, communication networks unreliable, and the threat from Axis powers looming. Success was not guaranteed. This tension, the pressing need for accurate weather forecasting, the technological uncertainty, and the looming global conflict set the stage for IBM's pivotal innovations. What began as a simple pursuit of information would soon reshape the very way America approached warfare. The urgency of this endeavor naturally leads to the second section, where military pressures, Axis capabilities, and government initiatives push the radar network from concept to reality. As 1941 progressed, the U.S. military grew increasingly aware that weather could no longer be treated as an afterthought. The Atlantic Ocean, wide and unforgiving, had become a deadly theater for convoys and naval exercises. Storms could scatter formations, damage ships, and turn routine missions into tragedies. Yet, unlike Germany or Britain, the United States had no comprehensive network capable of tracking these hazards. Reports trickled in from coastal stations, merchant ships, and sporadic reconnaissance flights. But by the time the information reached Washington, it was often outdated. The Axis powers exploited this advantage ruthlessly. German meteorologists embedded in the Luftwaffe and Kriegsmarine utilized both high-altitude observations and early radar to anticipate North Atlantic conditions. Weather data influenced submarine patrol routes, air raids, and even supply shipments. The Allies had begun to recognize that controlling information about the skies could be as decisive as controlling the seas. U.S. military planners realized that without similar capabilities, any large-scale operation, be it troop movements or convoy protection, risked unnecessary loss. Government leaders, including officials at the War Department and the Bureau of Standards, began convening specialized committees. The goal was clear: accelerate the development of radar-based weather forecasting and integrate it with a nation's growing computational infrastructure. Funding was allocated to expand existing laboratories, purchase radar components, and recruit skilled technicians. IBM, with its reputation for precision and industrial reliability, was a natural partner. Its tabulating machines could handle enormous data sets, processing readings from multiple radar stations to produce coherent forecasts. The collaboration marked one of the first large-scale intersections of private industry and military science in U.S. history. Yet the challenge was more than technical. Radar stations needed to be strategically placed along the eastern seaboard to cover the Atlantic approach, while ensuring redundancy in case of mechanical failure or enemy sabotage. Each station required trained operators, constant calibration, and a secure line of communication back to central processing hubs. The military also demanded real-time updates, pushing IBM engineers to redesign machines to handle continuous input rather than batch processing. It was a monumental task, requiring synchronization across geography, technology, and human expertise. Amid these logistical hurdles, the human stakes remained clear. Navy officers monitoring the Atlantic understood that each storm front could disrupt convoys carrying troops, fuel, and munitions to Britain. Army planners knew that training schedules and early deployment exercises depended on reliable forecasts. Scientists and engineers labored in unheated labs, often through freezing nights, recalibrating delicate radar equipment and testing novel algorithms on IBM tabulators. There was little margin for error, and failure could mean catastrophe. By the summer of 1941, preliminary radar stations began transmitting their first meaningful readings. The data, when fed into IBM machines, revealed storm patterns that had previously been invisible to forecasters. While the forecasts were not yet perfect, they offered a glimpse of the transformative potential of combining computation with meteorology. Military leaders took note. Operations could now be planned around the weather rather than in spite of it. This confluence of technological innovation, human determination, and strategic necessity set the stage for an entirely new form of warfare. America was learning to harness information as a weapon, anticipating conditions before they became threats. IBM's radar initiative was more than a scientific experiment. It was a bridge between the chaos of nature and the precision required by modern conflict. With these foundations in place, the story opens multiple perspectives. The engineers who designed the machines, the commanders who relied on their predictions, the military planners under pressure, and even the Axis forces watching from afar. Each angle reveals a different dimension of the same historical moment. In the freezing halls of early 1941 laboratories, human determination was as vital as any machine. Engineers and technicians worked long hours, sometimes in near darkness, adjusting fragile circuits and measuring storm signals that danced invisibly across the Atlantic. There was a quiet tension in the air, an awareness that their calculations could save lives or fail catastrophically. One young meteorologist, hunched over a tabulator, traced the movement of a storm front with a pencil on a plotting chart, each line representing miles of ocean and thousands of potential lives at sea. Their work was meticulous, repetitive, and often exhausting, yet it carried the weight of national security. In the quiet hum of machines, the human element was ever present. Focus, intuition, and the relentless drive to make sense of chaos. IBM's machines were the heart of the operation. Tabulators, originally designed for census calculations and business records, were repurposed to process vast streams of meteorological data. Each input, barometric pressure, wind speed, temperature readings from coastal stations, was converted into punch cards. These cards were fed into the machines, which could perform complex tabulations far faster than any human. Radar, still in its infancy, supplied a constant flow of raw observations. Antennae rotated slowly, bouncing radio waves off distant cloud formations, detecting moisture and precipitation patterns invisible to the eye. The combination of radar detection and IBM computation represented an unprecedented technological synergy. Mechanical precision meeting electromagnetic insight, producing forecasts that were more accurate, faster, and actionable than ever before. For military planners, the implications were immediate. Storms no longer had to be a blind threat. Naval convoys could adjust their routes to avoid deadly gales. Training exercises could be scheduled to minimize risk. In early July 1941, a test forecast from a preliminary radar site correctly predicted a severe storm approaching the North Atlantic convoy routes. The information, fed through IBM machines, allowed commanders to delay troop transports by hours, preventing potential disaster. The tactical value of weather intelligence became clear. A nation that could anticipate natural forces gained a strategic advantage as tangible as any battleship or artillery battery. Weather forecasting had become a weapon in its own right. Each of these angles, the human endurance, the technological ingenuity, and the tactical necessity, intertwined to form a narrative of urgency and innovation. Engineers and meteorologists labored under immense pressure, their work amplified by machines that stretched the limits of contemporary technology. Military leaders, once constrained by uncertainty, now possessed foresight, allowing them to make decisions that had previously been impossible. These perspectives illuminate more than just the mechanics of radar and computation. They reveal the emotional weight of innovation, the stress, the hope, the relentless pursuit of precision. In laboratories and coastal stations, the human, technological, and tactical converged, forging a system that would redefine America's approach to warfare. The success of these early trials, however, was fragile. Machines could fail, antennas could freeze, and storms could surprise even the most diligent forecasters. Each challenge posed a question. Could human ingenuity keep pace with nature's unpredictability? This tension sets the stage for the second section of Angles, where leadership decisions, enemy observations, and ethical considerations come into sharper focus. Military and government leaders faced a dilemma. Invest in an unproven technology or risk lives and operations to uncertainty. The War Department and Navy leadership, acutely aware of the Axis's weather advantages, pushed for rapid implementation of radar networks. Meetings in Washington were tense. Generals and admirals scrutinized reports from engineers, debating placement of stations, allocation of resources, and prioritization of coastal coverage. Decision-making had to balance practicality with ambition. A single misstep, a misallocated antenna, a delayed data line, a malfunctioning tabulator, could nullify months of effort. Leaders relied on forecasts, not merely for planning exercises, but for national security, entrusting young engineers and IBM machines with outcomes that could alter the course of war. From afar, German meteorologists monitored Atlantic weather with precision, aware of its tactical value. The Kriegsmarine leveraged storm data to plan U-boat patrols, while Luftwaffe operations accounted for high-altitude conditions to minimize aircraft losses. Axis planners understood that controlling knowledge of the environment was as vital as controlling physical territory. If the United States could not match this capability, the balance of power in the Atlantic remained tilted toward the enemy. Unbeknownst to many in Washington, the race to predict storms was already a quiet front in the broader conflict, one where knowledge itself was weaponized. The endeavor raised profound questions about human reliance on machines. Was it ethical to entrust lives to calculations derived from circuits and punch cards? Engineers wrestled with this responsibility daily. Every card fed into an IBM machine represented more than data. It symbolized the fate of convoys, air crews, and potentially thousands of civilians dependent on supplies crossing the Atlantic. Yet necessity justified innovation. In the tension between uncertainty and foresight, humanity confronted its own limits, embracing technology not as a crutch, but as an extension of intelligence and moral responsibility. This convergence of ethics and ingenuity defined the character of the project and the era. These angles collectively illuminate the broader narrative. Leaders pressed forward, balancing risk and reward. The enemy's own weather capabilities cast urgency over every calculation, and human beings wrestled with the implications of surrendering judgment to mechanical processes. Together, they paint a portrait of innovation under pressure, where stakes were tangible and consequences immediate. By examining these angles, one begins to understand the multidimensional significance of the radar initiative. It was not merely an engineering challenge or a tactical tool. It was a crucible in which human courage, technological audacity, and strategic necessity were tested. The successes, failures, and decisions made during this period would culminate in a decisive turning point, where the potential of IBM-powered radar forecasting would be proven on the field of operations. Summer 1941. The Atlantic swelled with storms, and every cloud became a question mark over an ocean already fraught with danger. Radar stations, hastily constructed along the eastern seaboard, began transmitting their first operational readings. Massive IBM tabulating machines hummed in synchronized precision, processing punch cards that represented winds, pressures, and precipitation from dozens of coastal and offshore points. Engineers monitored the outputs, adjusting dials and recalibrating antennae as the first forecasts emerged. Every misalignment, every delayed reading carried consequences. On July 12, 1941, a test forecast predicted a violent storm moving from the North Atlantic toward a critical convoy route. The forecast suggested high winds and turbulent seas, conditions that could scatter ships and leave them vulnerable to enemy submarines. Naval officers convened urgently in Washington, examining the radar-based predictions with a mix of skepticism and awe. To this point, such precise forewarning had been impossible. Surface reports often arrived too late. Old meteorological methods could not anticipate the storm's speed or trajectory. Now, for the first time, America could plan in advance rather than react in panic. The technical challenges were immense. Radar signals were distorted by rain, snow, and atmospheric interference. Tabulators occasionally jammed under the volume of data, and human operators risked errors while transferring readings to punch cards. But through hours of meticulous work, the machines processed the information, generating actionable forecasts. Engineers traced the storm's path on plotting boards, markers tracing arcs and vectors over maps of the Atlantic. Officers compared these predictions against naval intelligence, cross-referencing positions of convoys, U-boats, and training exercises. Every decision hinged on the accuracy of a network still in its infancy. For the personnel involved, the stakes were intensely personal. Radar operators stood on windswept platforms, exposed to cold and electrical hazards, their eyes fixed on screens and spinning antennae. Engineers worked in cramped, overheated machine rooms, listening to the rhythmic clatter of tabulators and the occasional buzz of misfiring relays. In Washington offices, officers argued over delaying convoy departures, balancing operational urgency against the threat of storms. Lives were literally in the balance, yet no one could fully predict the outcome. When the convoy sailed under the guidance of the radar forecast, the storm arrived as predicted, but with a twist. Initial readings had underestimated the storm's intensity near the southern flank. Quick adjustments from the radar team, using real-time updates processed by IBM machines, allowed the Navy to reroute ships, avoiding the brunt of the gale. Observers onshore watched the vessel stagger through heavy seas. Yet remarkably, no ships were lost. Commanders noted the forecast's effectiveness in dispatch reports. The predictive work of coastal radar stations prevented catastrophic losses. Further integration is recommended. The success was exhilarating, but it was not without tension. Each forecast became a trial by fire, testing the limits of machines, human judgment, and coordination. Technical failures were frequent. A malfunctioning antenna could erase hours of data. A card jam in a tabulator might delay a forecast by precious hours. Engineers improvised repairs on the fly, often working through nights of snow and wind, their hands numb and minds alert to the smallest error. Yet each correction reinforced confidence in the system. What had begun as a theoretical experiment was now proving its practical value. Beyond the technical and operational dimensions, there was a psychological shift. Military leaders began to trust the forecasts. Officers accustomed to reacting to chaos now plan around it. Convoy schedules, training exercises, and even aircraft patrols could be adapted in advance. The storm was not merely weather. It had become a test of human ingenuity, industrial coordination, and technological ambition. IBM's tabulating machines and radar stations were no longer laboratory novelties. They were instruments shaping the real-world outcomes of war. The climax of this phase was not a single moment, but a crescendo of successful predictions, human perseverance, and technological validation. By August 1941, the radar network and IBM systems had demonstrated consistent value, earning full military commitment. Yet the story was far from over. The stakes were about to escalate, with wider deployments, larger data sets, and more complex storms challenging every assumption. The second section of the climax will show how the system reached full operational maturity and altered strategic decision-making on a larger scale. By late 1941, IBM radar stations were no longer isolated experiments. They formed a continuous network along the eastern seaboard, feeding a constant stream of data into central processing hubs. Tabulators ran day and night, spitting out forecasts for storms hundreds of miles offshore. Engineers had developed routines for rapid card processing, error checking, and real-time recalibration of antennae. The system, though still primitive by modern standards, could now anticipate storm trajectories with unprecedented accuracy. The stakes escalated on September 3, 1941. A massive North Atlantic storm threatened a convoy transporting critical supplies and troops to Britain. Radar stations detected the storm's formation, while IBM machines calculated its speed and angle of approach. Military officers convened, cross-referencing the forecast with intelligence on U-boat positions. The calculations indicated that if the convoy proceeded along its planned route, ships could be scattered across hundreds of miles in seas exceeding 30 feet. Yet rerouting would delay delivery schedules and expose vessels to potential enemy action. The tension in the command room was palpable. Officers debated options, their eyes flicking between radar readouts, plotting boards, and IBM tabulators humming in the background. On the East Coast, radar operators monitored spinning antennae, noting minor deviations in the storm's predicted path. Technicians worked feverishly to recalibrate equipment, feed fresh data into tabulators, and produce updated forecasts. Outside, coastal winds rattled towers and power lines, a reminder that nature remained untamed and unpredictable. Ultimately, the forecast prevailed. The convoy altered course, navigating a safer route that avoided the storm's core while maintaining operational timing. Reports later confirmed the success. Ships arrived intact, cargoes preserved, and no personnel were lost to the elements. Officers praised the radar and IBM teams in dispatches, noting that the combination of real-time meteorological observation and rapid computation had averted disaster. For the first time, technology had truly extended human foresight over the vast Atlantic. The operational success had ripple effects. Confidence in the system encouraged expanded deployment. New radar stations were commissioned further north and south along the coast, while IBM engineers improved tabulator capacity to handle more complex data sets. Forecasts became increasingly sophisticated, incorporating wind shear, precipitation intensity, and early tropical disturbances. Military planning, from convoy scheduling to air patrol routes, now relied heavily on these forecasts, transforming decision-making from reactive to proactive. The human dimension remained central. Engineers worked long shifts. Technicians battled fatigue and freezing conditions, and officers adapted their strategies to the rhythm of the data. Morale improved as successes mounted, yet everyone understood the stakes. Failure could still result in disaster. There was an unspoken pride in the quiet victory of information over uncertainty. The success of IBM radar forecasting was not measured in explosions or territorial gains, but in lives saved, missions completed, and the invisible mastery of natural forces. At the same time, the Axis powers took notice. German meteorologists had long relied on the predictability of Atlantic storms to guide U-boat patrols and Luftwaffe operations. Now, American forces could anticipate weather with a precision previously reserved for their adversaries. While the Axis would continue to pose formidable threats, the radar network marked a strategic leveling of the playing field. Intelligence itself had become a weapon as potent as any battleship or aircraft. The climax of this innovation was both technical and human. IBM's machines, the radar stations, and the operators who maintained them had transformed a theoretical capability into a practical instrument of war. Convoys could sail with reduced risk, exercises could be scheduled with confidence, and operational planning could account for nature itself. The tension, the nights of relentless work, and the delicate interplay between human judgment and mechanical computation had culminated in a decisive turning point. America could now predict the unpredictable, and in doing so, had gained a subtle but critical advantage in the Atlantic theater. As the storm clouds cleared and the convoy arrived safely, the United States realized that the lessons of radar and computation would extend far beyond a single battle or storm. This success paved the way for a new era of integrated technology, human ingenuity, and military strategy. Yet with triumph came responsibility, the need to maintain, expand, and continually improve the system to face an uncertain and ever-evolving conflict. By the end of 1941, the first operational IBM radar network had proven its worth. Convoys across the North Atlantic, once vulnerable to both storms and enemy submarines, now benefited from early warnings that allowed for precise rerouting. Naval officers reported a marked reduction in weather-related losses. In one dispatch, a convoy commander noted, "Radar and computation have given us sight where none existed." The difference between risk and safety is now quantifiable. This sentiment reflected a profound shift. The ability to anticipate natural hazards had become a strategic advantage, not merely a convenience. The success of the system reinforced collaboration between the military and private industry. IBM's engineers, who had once labored in relative obscurity, now became indispensable partners in national defense. Their tabulating machines, combined with radar inputs, demonstrated that computation could extend beyond finance, census work, or industrial logistics into the domain of life and death decisions. Laboratories expanded, additional operators were trained, and coastal installations multiplied. Each new station added redundancy and coverage, transforming the radar network into a resilient system capable of continuous monitoring. Military planners quickly recognized that operational success depended not only on technology, but on human coordination. Officers had to interpret forecasts, make swift decisions, and adjust operations dynamically. Engineers and operators remained on constant alert, maintaining equipment under extreme conditions and troubleshooting errors in real time. The human and mechanical elements were inseparable. One without the other could compromise the system. This interdependence set a precedent for future military technological initiatives, illustrating that innovation required both ingenuity and disciplined execution. Beyond immediate tactical advantages, the radar initiative influenced broader strategic planning. The U.S. Navy and Army began to incorporate weather forecasting into operational doctrine. Training exercises, once canceled unpredictably due to storms, could now be scheduled with confidence. Supply lines to Europe, which relied on precise timing and coordination, became more reliable. Commanders gained a sense of control over variables that had previously been uncontrollable. In essence, a new dimension of warfare had been added: information as a force multiplier. Public awareness of the program remained limited, yet reports of successful forecasts filtered through military and civilian channels. Weather forecasting was increasingly seen as a matter of national security rather than a purely scientific endeavor. Newspapers occasionally referenced the new predictive capabilities in general terms, while military reports emphasized efficiency, reduced risk, and enhanced coordination. The concept of combining mechanical computation with environmental observation was now validated and celebrated. laying the groundwork for further technological integration in wartime. The success of the radar network also had a psychological impact. Officers and crews developed confidence in forecasts, knowing that storms could be anticipated and mitigated. Engineers took pride in their role in safeguarding lives, while operators experienced the satisfaction of seeing abstract data translated into tangible outcomes. For a nation on the brink of global conflict, the ability to master environmental uncertainty was more than a technical achievement. It was a morale booster, a proof that American ingenuity could rise to meet unprecedented challenges. Yet these gains came with cautionary lessons. Failures in early stations, equipment malfunctions, and the constant threat of extreme weather demonstrated that the system was not infallible. Each success highlighted the importance of redundancy, continuous maintenance, and rigorous training. The military learned that technological advantage required not just invention, but sustained operational discipline. These lessons would inform future expansions of the network and the integration of more sophisticated computing machines as the war progressed. As the radar stations expanded and IBM's role solidified, the U.S. began to experience a broader transformation in how it approached warfare. Technology, human expertise, and strategic planning were no longer separate domains. They were a unified system capable of shaping outcomes in ways previously unimaginable. This immediate aftermath set the stage for long-term consequences. Expanded infrastructure, increased industrial coordination, and the emergence of computation as a cornerstone of military capability. The initial successes, however, were only the beginning. The true scope of the radar initiative's impact would become apparent as America fully mobilized for war, confronting more complex operations, larger convoys, and more severe weather events. The second section of Aftermath will explore these long-term consequences, the rise of IBM as a strategic partner, and the enduring legacy of the radar program. As 1942 approached, the initial radar network had grown into a robust and indispensable tool for the U.S. military. Coastal stations extended north to Maine and south to Florida, creating near-continuous coverage of the Atlantic seaboard. Data flowed seamlessly into IBM tabulating machines, which had been upgraded to handle increasing volumes and complexity. Forecasts could now predict not only the path of storms, but their intensity and potential impact on specific convoy routes. Military operations, once dictated by uncertainty, became informed by precise, actionable intelligence. The ripple effects were significant. Convoy losses to storms decreased dramatically, allowing critical supplies, fuel, and troops to reach Europe on schedule. Air crews benefited from improved weather intelligence, reducing flight cancellations, mishaps, and unnecessary risk. Naval exercises and training programs, previously disrupted by unpredictable conditions, now adhered to planned timelines. The military had effectively neutralized one of nature's most formidable obstacles, transforming weather from an unpredictable hazard into a manageable variable. IBM, for its part, solidified its reputation as a key strategic partner. Its tabulating machines and the engineers who maintained them became central to military planning. The success of the radar network demonstrated the practical value of industrial computation beyond theoretical applications. IBM's collaboration with the military set a precedent for public-private partnerships in defense technology, laying the groundwork for post-war innovations in computing, logistics, and intelligence. Engineers who had once calculated payrolls were now calculating the movements of storms and the safety of convoys, illustrating a dramatic expansion in the scope and impact of their work. Strategically, the radar initiative shifted the balance of information in the Atlantic theater. U.S. forces could anticipate and avoid hazards that had previously given adversaries an advantage. German meteorologists, who had long relied on knowledge of the unpredictable Atlantic, now faced a foe capable of foreseeing the weather with increasing accuracy. The intelligence gained from the radar network became a force multiplier, enabling commanders to make informed operational decisions and reduce risk to personnel and material. The program's influence extended beyond immediate military operations. It transformed how the United States approached problem-solving in complex, data-driven environments. The collaboration between scientists, engineers, and military leaders illustrated that technological innovation could overcome limitations previously accepted as natural law. Data-driven forecasting became a model for future military and civilian applications, from logistics to strategic planning, highlighting the enduring value of combining human expertise with computational power. Yet the initiative was not without its challenges. Continuous maintenance of radar stations was essential, and extreme weather, equipment wear, and human error occasionally disrupted forecasts. Engineers and operators worked long shifts, often under harsh conditions, to ensure uninterrupted service. These ongoing efforts underscored the lesson that technological breakthroughs required sustained operational commitment, not merely ingenuity in invention. The resilience and dedication of personnel were as crucial to success as the machines themselves. By late 1942, the full scope of the radar network's impact was undeniable. It had reduced operational uncertainty, enhanced convoy security, and elevated the strategic value of meteorological intelligence. The initiative had also demonstrated the potential of industrial computation in real-time, practical applications, influencing post-war planning in both military and civilian sectors. IBM's involvement foreshadowed the rise of computing as an integral part of national security, while the successful integration of radar forecasting marked a pivotal moment in the evolution of modern warfare. As the nation prepared for wider engagement in global conflict, the lessons of the radar program endured. Innovation required collaboration, foresight, and relentless attention to detail. The successes of 1941 and 1942 were more than technological achievements. They were proof that human ingenuity, guided by accurate information, could turn uncertainty into advantage, laying the foundation for the future of warfare and computation alike. The story of America's first operational weather radar network naturally leads to a moment of reflection. What this innovation meant not just for strategy, but for humanity's ability to master nature and anticipate the unpredictable. The storm clouds of the Atlantic were more than weather. They were a test of foresight, ingenuity, and human will. In 1941, America faced not just an enemy overseas, but the unpredictable force of nature itself. Without a coherent weather forecasting system, every convoy, every training exercise, and every naval deployment was a gamble. Yet, through the quiet determination of engineers, meteorologists, and military officers, uncertainty was transformed into insight. IBM's tabulating machines, paired with radar stations along the coast, became instruments of clarity, translating raw data into decisions that saved lives and preserved operations. The story of this innovation is a story of human adaptability. It is about engineers working through freezing nights, operators interpreting signals that no one had ever trusted before, and commanders learning to plan around predictions rather than reacting to chaos. It is about the courage to rely on machines while never letting human judgment fade. In this fusion of intellect and technology, the United States discovered a new dimension of warfare, one where knowledge itself became a weapon. Beyond the immediate military impact, the radar initiative foreshadowed the future. It demonstrated that computation and observation could extend human perception, allowing humanity to anticipate, rather than merely respond to, the forces of the natural world. It set a precedent for public-private collaboration in technology, laying a foundation for modern computing, meteorology, and data-driven decision-making. In the quiet after the storm, as convoys reached their destinations intact and radar operators finally rested, there was a profound realization. Mastery over information could rival mastery over weaponry. The lessons of 1941 endure, reminding us that innovation arises where necessity meets courage, and that the human drive to predict, understand, and act can turn even the most formidable uncertainty into advantage. In the end, America's first weather radar network was more than a technological breakthrough. It was a testament to human resilience, foresight, and the enduring pursuit of control over the uncontrollable. It changed the course of war, and it changed the way we perceive our ability to navigate the unpredictable world around us.